Great. Starting off strong.
You don't need it. It works without.
Yeah, really? Yeah. It's fine. Let's put it here.
You have that on? I will. How do you make this sound? You have to put the, you have to hit it at the top. Okay. Okay, good afternoon. I welcome everybody to the last set of talks of the second day of this meeting. I think we are all already tired. We are not used to being so long in meetings. We are more used to be like online with the little squares. So it's a pleasure to introduce Mark Iwen or Iwen. I don't know how
Iwen,
you
yeah,
pronounce
sure.
it.
Iwen works.
Iwen, and he will talk to us about low distortion embeddings of submanifolds of R big D, lower bounds, faster realizations, and applications. I took away.
Yeah,
Okay.
thank you. Yep. Thanks for the introduction, for the invitation, and for sticking with it until, past 4 p.m. All good things. Yeah, so I'm going to start off with something that I hope is easy or quite familiar because it's 4 p.m. And when I confuse you because I say something that doesn't make sense, just ask a question because, it's going to happen. All right, so anyways, we're interested in low distortion embeddings, effectively generalizations or sort of variations of the Johnson-Lindenstrauss lemma. So here is the old theorem that we have been using so much. Says we have a finite set S, right? Just fixing notation. There's going to be a matrix with m rows that doesn't distort any of the pairwise differences of the elements of your finite set very much up to this distortion parameter epsilon, right? So very nice. And we know from the original work and the many variations that have come after that you can do this with a number of rows that scales 1 over epsilon squared times the log of the cardinality of this finite set, right? And there are many nice applications in data science because there are random matrices that give this to you, which are oblivious, which means I don't have to know anything about the set I'm embedding, just have some idea of what the cardinality bound is, and I'll still win. It's very nice. There are many families of randomized embeddings that work for you. You can use very unstructured matrices like Gaussian random matrices, and they'll work. You can use very structured matrices and they'll work, and you'll have fast matrix vector multiplies. So here RFD, this is a random diagonal matrix, a discrete Fourier transform matrix, and then a random selection of some rows. So this is something that Felix has done work on. We know that those will work. And we are mostly interested in this talk in taking this usually finite set S and making it into an infinite set, in particular, an infinite set with a lot of geometric structure, and considering similar types of embedding results, both upper and lower bounds. So that's what I want to talk about today. And we know there are lots of applications there. So if I let my finite set instead be just an infinite set, but a simple one, a subspace, I again don't have to know much about the subspace and I can still embed it, high probability. Tons of applications in numerical linear algebra, as you can imagine, because of this very nice property. I could make S all the sparse vectors, and then I have compressive sensing, RIP constructions, basically. And again, what I'm going to focus on more here are making this infinite set a submanifold of RD and talking about what happens in that case, and then relating this number of rows you need to some geometric parameters of the submanifold. Okay, so again, probably review, but it's 4 p.m. We have infinite sets we're interested in. We shouldn't be talking about cardinality probably because that's going to be awkward. So we'll instead use the Gaussian width of a set to sort of characterize its complexity and tell us how many rows we need in order to obtain a low dimensional embedding of this type. So it's going to replace the cardinality in the types of results we're interested in using for embedding sets. And then we can remind ourselves of all these nice sort of facts about Gaussian widths of sets that we have. So if we have a finite set, it's going to be at least always upper bounded by the square root of the log of the cardinality. So the Gaussian width squared looks like the log of the cardinality that appeared in our embedding result. For a subspace, it's a square root of D, a little D-dimensional subspace. When we have S sparse vectors, it's a square root of S log D over S, which looks like what we know the number of rows should be, right? And so there are these nice embedding results that say you have a sufficient condition is that you need something like the Gaussian width of the set squared over epsilon squared. And then if you have a sub-Gaussian matrix, you can preserve the set, right? And then you get your RIP results and everything else. So this is the right sort of measure that we're working with. So first thing well, a little bit more detail, right? So a little bit more detail about that result. This is out of Vershinin's book, effectively slight modification of something there. You take your set S, you can normalize it because you're talking about a matrix that you're using for embedding, so normalize away. And then the Gaussian width of the normalized set is going to sort of tell you how complex the set is, how many rows you need in order to embed things. And if you add in a few extra rows, you can increase the probability that you get this preservation of all the pairwise distances. So, right. And then again, talking about faster, more structured embeddings, more reminding you of things you already know. You can use more structured matrices and still get away with doing things like this. You can do these subsampled Fourier constructions, for example, using results by Oymak, Recht, and Sultan al-Khattabi, for example. And you just pay some additional log factors on your embedding dimension M, but you still get away with everything you want. Okay, so we know about this stuff. So something a little bit less maybe well-known in the community are these sort of lower bounds that tell you. So these give you conditions that allow you to succeed, right? That suffice. Then you can ask how tight are these results in terms of the embedding dimension. So there's been previous work on this for finite sets, and it's particularly nice because it also deals with arbitrary maps, which are not necessarily linear, and sort of tells you that you still have what you would expect in terms of the embedding dimension. So here's a nice theorem by Jelani Nelson and one of his collaborators. It says I get to pick a cardinality of my set and some Euclidean space that it's going to sit in. And then there's a set that hits that cardinality in that Euclidean space such that any function that embeds it into Rm with our sort of by Lipschitz embedding of the differences that we want must have a number of rows that scales logarithmically in n and like 1 over epsilon squared. So even if you consider nonlinear maps, you have to use this number of rows up to constants. So sort of very surprising to me anyways, even comparing to nonlinear maps, linear maps, at least with respect to this embedding dimension, are sort of optimal to constants, right? Just kind of shocking to me, which is why I think I got interested in this. So the way this lower bound works, it builds this worst case set that achieves this. So it says there exists a set where you have to do this. So, right, there's a bad set. It shows this sort of that linear embeddings almost are as good as you can do, right, which is interesting. Some questions it doesn't answer are how common these sets are that force you to use this number of rows, right? So it says there is a worst case set. What if I'm interested in sets of a particular class that have some geometric structure, right? That's not an arbitrary set that has been designed for me. So how well can I do if I know what sort of set I'm interested in? You know, what about infinite sets? These are cardinality bounds. So what about infinite sets? What do we have? There should be something similar. And probably more difficult, there's this lower bound on epsilon. So there are some questions about what happens when epsilon gets smaller. Does it still, you know, sort of work? So thought about this a little bit with my graduate student, Armand Tevicoli, and colleague, differential geometer at MSU, Ben Schmidt, and have the following lower bound that sort of partially addresses some of these questions. So it says, again, you have any function you want that obtains your embedding result, potentially nonlinear, so you don't really assume anything else about it. Then the number of rows you need in order to guarantee that this happens for all the pairs of points in your set S has to scale quadratically in the Gaussian width of S, which is sort of what you would expect. And there's some additional sort of punishment from the diameter of S and some decorations involving epsilon. Okay, so at least for epsilon that are not too small, this effectively generalizes the Nelson, et cetera, result to finite sets, right? You just plug in the Gaussian width of bound for finite sets. The fact that there are finite sets that have that, that approximately achieve that, and you get something similar. Again, it shows that sub-Gaussian embedding results involving Gaussian widths are sort of almost optimal, at least up to these extra diameter decorations and things, even comparing to nonlinear functions, which again is sort of strange. And the thing that we care about most here is that this is for any particular set S. So you can make more constrained classes of S, and this will still apply, for example, S's that have geometric structure because they happen to be manifolds or something, which is going to be useful. One thing that this doesn't have, you notice the epsilon dependence is screwed up, right? So there are at least some cases where this should definitely be a 1 over epsilon squared. In general, it would be interesting to know what the epsilon dependence should be doing. That would be an improvement that would be interesting, I think. Anyways, so we're interested in these more general classes of S. So what are we going to specifically sort of focus on here? We are going to think about smooth submanifolds are going to be little d dimensional. So little d is going to be quite a bit smaller than the Euclidean space that they're sitting in, right? And the geometry is going to be sort of quantified or controlled with respect to this concept of reach, which I don't expect anyone to know about or remember. So I will now make sure you, maybe if you decide to, learn one thing in this talk, which is what the heck reach is. Okay, so what is reach? And why might it control the geometry of a set like this? So I'll do it slow. So let's look at the distance function to anything in our manifold, our surface, our subset, whatever you want. Right, just looking at the closest point in the manifold and looking at the distance to that point. Then the projective domain is just going to be the set of X where there's a unique minimizer that achieves that distance, right? Or sort of more geometrically, put a ball around the X that you're wondering about being in the projective domain, grow the ball until it touches the surface. If it hits it, the first time it touches it in one unique place, it's in the projective domain. There's a unique nearest neighbor. So, right? And then you can immediately see things, right, like points and subspaces, as we already know, have the entire Euclidean space in their projective domain. And you start seeing maybe for slightly more interesting shapes why curvature would affect this projective domain and why knowing something about this domain would let you sort of say something about the curvature. So here's two examples. Here's a circle, right? This is my M. And this green point is in the projective domain. I grow a circle around it and it touches the other circle in one exact spot. Same thing here. The only problem I have is at the origin. When I grow a circle, I hit the entire circle at the same time. So everything except for the center of the circle has a unique projection. And slightly more interesting example here, I have a one-dimensional curve. It's sort of flat over here. This green point again touches it in one spot. Here, I grow my ball around this red point, and the first time it touches this curve, it touches it in two points, so it's not in the projective domain, right? So places where you have a lot of curving, a lot of curvature going on locally, kill your projective domain. Non-linear, non-smoothness, like a corner, will kill it. You'll eliminate all of the points close to the corner. So knowing something about this projective domain tells you about the curvature, tells you about the smoothness, right? That's why you learn things about this thing. Okay, so what is reach again? So if I put a tube around my manifold, so I just consider all the points that are in a tube around of distance r, so it's a tube of radius r, the reach is just the largest tube that's contained in the projective domain. So it tells me about, right, every point that's within that distance of the manifold has a unique nearest neighbor on the manifold. Think of it that way. So there we go. This is a fun sort of definition. If you've already can barely stand listening anymore, here's a homework problem for you to work on while I continue to talk and you ignore me. You can characterize really nice sets using reach. So the reach of a subset of Euclidean space is infinite if and only if it's a closed and convex set. There's a little homework problem for you to do if you want. Generally, right, the larger reach is, the simpler, flatter, less self-intersecting, etc. The set is going to be. So less close coming to self-intersecting. All right, so some more pictures because it's 4 a.m. The tubes around this line segment as sort of a manifold, one-dimensional manifold with boundary, look like pills. You can grow them forever. So it has a reach that's infinite. It's closed and convex. The reach of the sphere has, right, the missing point. So it's it's equal to the radius of the sphere. The last tube is this fat tire that starts touching at the origin, and then you're done. Okay, all right. So manifold embeddings, right? They've been done before by Baranuk and Waken, his student, Efficatari. So they have this theorem from an Acha paper. Let's take a look at it. It involves reach. So it says, if you have a d-dimensional submanifold and you assume that the volume of your manifold compared to the reach raised to the dth power satisfies this condition, then you get this embedding property that we've been talking about for all pairs of points in your manifold. If your dimension scales the way you expect it has to in the dimension of the manifold, and times some additional log factors involving the reach. The manifold gets crazy as the reach goes to 0. This blows up. It sort of makes some intuitive sense. Your manifold does strange twisting off towards infinity, so has a big volume. Your dimension potentially blows up. Right, it sort of makes sense. So what's wrong with it if it's so nice? I really like it. It is nice. Nothing's wrong with it, but this is for manifolds that don't have boundary. So you better be talking about something like a sphere or an ellipsoid or something like that. As soon as you have a surface that has boundary, this doesn't apply. The techniques don't apply anymore. It would be nice to have a generalization where it did. This condition's kind of weird. Why is it there? Do we need it? Maybe we can get rid of it. And going back to the lower bounds, you can ask, what can I say? What if I don't use a matrix with a small number of rows? What if I use any arbitrary function? How optimal does this thing look? Can I say anything about what that is going to look like? So the lower bounds question first. Here is a corresponding result that builds off of the last little theorem that we saw. Running out of time already, I guess. So, right, any function that yeah, okay, that's right. Yeah, I don't remember, but I believe you. Yeah. Anyway, so an arbitrary function into Rm that satisfies our condition that we care about, right? There are two regimes for this lower bound. One is where the reach is large compared to this quantity. This little guy right here is the volume of a little d-dimensional unit ball. So this is sort of like some kind of ratio between the volume of the manifold and a ball and some extra decoration. So when the reach is bigger than that, so bigger than that means simple, flat, not self-intersecting, like a subspace sort of situation. If it's bigger than that, you have a required embedding dimension that looks like this. It has to scale like d, some decorations involving the diameter of m that pop up. And the volume can still kind of get you a little bit, but if you do something like make this, consider a ball, it disappears, and you get your radius sort of canceling this thing out, and you start seeing that things make sense, in particular, variations there. The other case is reach is going to 0, weird, crazy, almost self-intersections, wild curvatures happening somewhere. God knows what's going on. The lower bound sort of breaks down to some extent, but when the reach is not too ridiculously small, you have something that starts saying, again, you need this type of logarithmic behavior that we saw in Waken's result. Some additional, linear scaling in D, which you certainly hope was there. Things that seem to make some sense, right? And this is actually compatible with their initial theorem. So this assumption is compatible with the crazy case. So it actually, an arbitrary nonlinear f has to satisfy this. And if you compare this to what they had, it's sort of off from this lower bound by reach squared over diameter squared. So up to that parameter, for whatever manifold sort of makes this as large as possible, it sort of says that, again, their linear embedding might be at worst that bad compared to the worst nonlinear map in terms of preserving these things. Okay, so good. And the upper bound. So scary wall of text, you can also generalize their upper bound, get rid of or accommodate boundary if it happens to exist, get rid of the condition that was there, things like that. So what does this say? If you use a sub-Gaussian random matrix, You can, yes. You can have boundary if you want. It can be empty, so it is a generalization. You take the reach of your manifold. It's also going to depend on the boundaries reach. So we have the reach of each component of the boundary. They can be several, right? There could be a few holes punched into this thing, for example, though there can only be a countable number. You take the minimum of all of those reaches and the reach of the manifold. That's our tau now. You look at volume bound comparisons between your manifold and its boundary with the appropriate Euclidean balls. Decorate them with appropriate powers of reach in each dimension. Square those things, stuff them into the square root of a log. That's the number of rows you need in your sub-Gaussian random matrix. Again, says it's hard to write it more simply, but it removes that condition and allows boundary to appear in that nice Waken result. So that was about sub-Gaussian matrices. You can also do this for matrices with fast matrix vector multiplies. Prove similar bounds where you have some additional log factors that decorate the M as you would expect. But now you have matrix vector multiplies that are D log M you can achieve. So M being the embedding dimension, D, remember, is what any of the vectors on this, is the size of any of the vectors on this submanifold. So this is like a fast matrix vector multiply, FFT like matrix vector multiply for things that embed this submanifold. A little bit about the proof in the last 3 minutes, clearly non-exhaustive discussion. It's just two things basically. So you need some embedding results in terms of Gaussian width. You can take existing ones or prove some other ones about fast matrices with fast matrix vector multiplies. And then what else you need? You need some estimates for the Gaussian width of the unit secants of a manifold with boundary. So what is that exactly? Maybe I'll sort of stop here. So it's just this, right? So we're talking about linear embedding. So I want to know how complex is this set if I take differences of points on this manifold, normalize them so I have something on the ball, I can complete it so it's a compact set. And then I want to know how complex this thing is, right? So I want its Gaussian width, and the way you can get at it, you can build an epsilon net for this thing. You end up using epsilon nets and covering numbers for the original manifold to help you. And you have to augment it because when X gets close to Y, you have something that starts looking like a tangent space, and then you have to actually realize you have a manifold and do something that involves geometry. So that's why you have to augment things and actually use some geometric results. And once you have nice nets and covering bounds, then you can bound the Gaussian width using like Dudley's inequality or whatever you like. And then you apply your embedding results based on Gaussian width and you're done. Right? So again, most of the geometry comes into getting these covering number bounds, and you have to consider for the lower and upper bounds, both lower and upper bounds of the covering number bounds for these guys. And all of the geometry that you need to think about comes into these denominators, where you need to think about the maximum amount of volume on the manifold captured by a small ball at a point on the manifold, and how much it eats up. And then, the worst it can be in terms of both a maximum and infimum, and that sort of tells you what you need. All right, 3 seconds over. Done.
Probably these 3 seconds you had because I took them in the introduction by reading the long title.
Yeah, it could be true.
Okay, are there any questions? Wow, yes. Emily?
Yeah, thanks for the great talk and the reviews for our 4 p.m. brains.
I also have a 4 p.m. brain, so that was good. Yeah.
So I have two questions. The first one is, I think it was around slide, well, I don't remember, it's where you had the not necessarily matrix mapping. Maybe I missed this because my 4 p.m. brain. Were there any restrictions on your F? Like what?
Oh, yeah. So the lower bounds, like Jelani's, well, doesn't really matter, I guess, like this.
Well, I meant more yours, but sure, that works too. Like what?
Oh, yeah. It's just a map that satisfies this for the set that you're interested in. So it has a sort of bi-Lipschitz, it satisfies this bi-Lipschitz condition for all points, all pairs of points in the set S. And
But
that's
I
the
guess,
assumption
is
of
it
the.
possible, I mean, being kind of by Lipschitz on a set, does that mean that you're actually a nice function on a space?
So does this assumption apply some other nicer assumption or sort of smoothness class or something? I guess
I just don't know how funky these. Fs are
that
gonna
would
be in
depend on
general.
the set, I guess,
Yeah.
right? I guess to some extent, if the set is really trivial, it probably doesn't say much at all. If the set is chosen in a very smart way, it probably means you have some very, I would say it depends on the set.
And then the other question I had, oh my goodness, I had it. Where did it go? Oh yeah, so just kind of seeing this in context, right? We're in this neural network land with all these different talks. Like, what about something that's kind of in between the Fs and the traditional Johnson-Linden Strauss of something that's combining a linear thing and like a component-wise nonlinear thing? Like, is there any sort of Johnson-Linden Straussy kind of?
There are terminal embedding results, which I saw a talk on at Simone's last workshop, one of the last workshops I went to pre-COVID. You can take a JL embedding, add an extra coordinate, doctor things up in just the right way, and then get this guarantee to hold for all pairs of points where you have one that's in S and another one that's in RD, anywhere in RD. Okay, and still work in progress with the student. You can extend those to infinite sets and apply those to manifolds as well. So that's something that I've been working on. That's something I'm working on finishing up right now. And then you have this weird situation where you can embed into a lower dimensional space and preserve all the distances from any point in the larger Euclidean space to a manifold in Rm, where M is like these dimensions we had for the submanifold embeddings. It's kind of crazy. And it lets you do stuff that maybe, I don't know. Anyways.
Also, but I didn't mean to give you an opportunity to advertise future work that way.
There's always danger.
So, I'm just wondering about the microphone. I'm just wondering about the following. So if I have something like a half sphere, then that's a manifold that has a beach. But I can also think of the ball, and I can apply a result for the ball that would then apply to the half sphere. So I'm wondering, like, where the trade-off is.
You mean if you consider the half sphere as a subset of the manifold that you embed? I guess the volume would be quite a bit larger if you had to complete every manifold with boundary to something that didn't have boundary in a way. And then you have to prove to me that you can do that without screwing up the reach and inducing some weird curvatures in order to do it. And it gets complicated.
If I complete it to a closed convex set, the reach becomes infinite.
Yeah, that is true. But if you do that, you're automatically lost to some, well, yeah, you're sort of automatically lost, at least with respect to our theorems here, because as soon as you create a convex set, this guy is gonna, it's gonna be like full volume somewhere. And this guy's gonna have a little copy of RD in it, and then you're dead. When you normalize these things, right, you normalize this, you're gonna end up getting the whole ball if you, Oh, so I thought you were going to convexify the whole thing and then try to embed it. Yeah, no, you could apply Waken's result if you complete it in a way that doesn't screw up. You have to complete it so it doesn't have boundary in a way that doesn't screw up the reach, right? The reach could get worse, and the volume is definitely going to get worse. So then you're sort of, my interpreting your question is asking, can I tell you when the volume is going to get worse enough that it's going to, defeat the boundary, whatever it looks like, and also whether you can even do it in a way that doesn't make the reach a lot worse. And I don't know. That's probably very, very problem specific. But yeah, you could do something like that, but I don't know.
Okay, I want to, yeah.
Just one thing out of curiosity. So when you define your embedding, quote unquote, with the A, it naturally extends. And so, right, I mean, I can plug in things from M, I can plug in things from off M. It doesn't matter. So is there some Whitney embedding theorem here in the background that gives you this lower bound? Because if you have a function, or if you have this map that gives you these nice Lipschitz properties, then you can extend it a little bit up, and that explains why it's so hard to make.
That could be. So the proof here doesn't use any like Whitney embedding sort of theorems or anything. It's more using it's based more on probabilistic techniques. So properties of Gaussian processes and sort of stuffing what F has to satisfy into a Gaussian process, comparing it to one to another one, and saying, you're going to have something go wrong if you happen to embed into a space that's too small. So that sounds great. If there's another connection that could sort of improve things, I would be happy to think about it more.
Okay, I will give some chance to somebody of the audience, which are not present, if somebody has a question. Okay, if not, we thank the speaker again. We have 2 minutes of the next talk.
Yep.